All right, so welcome to another deep dive, where we take one fascinating subject, take all the research that's out there, and give you the core insights you need, quickly and thoroughly.
You got it.
Our listener, you're someone who appreciates getting right to the heart of the matter. You love those aha moments without getting bogged down in all those unnecessary details.
For sure, for sure. Our goal here is to unpack complex topics, help you connect the dots, and make sure you leave with a solid grasp of what really matters.
Exactly. Today, we're diving deep into the intellectual journey of John McCarthy. He was a true giant in the field, right?
Yeah.
We're going to trace his pivotal work in AI, artificial intelligence, but then also his intriguing later exploration into quantum technology.
Interesting.
Yeah. And our roadmap for this whole deep dive is this insightful essay, John McCarthy, K.I. Pioneer mit Blick auf Quantum Technology. It was written by Jürgen Schnippet.
Great essay.
Yeah.
Really gets to the heart of McCarthy's contributions.
So our mission today is to understand how McCarthy's thinking, how it evolved over time from essentially defining modern AI to recognizing the profound implications of quantum mechanics, how it could change the future of computation. Even intelligence itself, right?
Big questions.
Huge questions.
Yeah.
All right, so let's start at the beginning. Let's start with McCarthy's background. So he was born in Boston in 1927, and he showed just incredible aptitude for mathematics and science really early on.
Early, yeah.
So much so that he was teaching himself from university textbooks.
What?
Before he even started high school.
Oh.
I mean, that speaks volumes about his inherent drive, right?
It really does. It highlights just this deep-seated curiosity.
Oh, yeah.
Natural talent, obviously. I mean, he went on to earn a bachelor's in mathematics from Caltech in 48, followed by a PhD in mathematics, specializing in topology from Princeton in 51. His time at Princeton was particularly formative. He was influenced by some huge figures in logic, guys like Alonzo Church, Kurt Gödel.
Wow. Those are big names.
Oh, absolutely. These individuals really laid the groundwork for his future thinking.
They definitely set the stage, I guess you could say.
Oh, yeah.
For his contributions. And so this robust foundation in mathematics and logic, it proved to be absolutely critical because, he, along with Marvin Minsky, Claude Shannon, and Nathaniel Rochester, they coined the very term artificial intelligence back in 1955.
Yeah.
During the Dartmouth Summer Research Project. At this moment, this is widely considered like the birth of modern AI, right?
Absolutely. It's like the big bang of AI, and what's key here, I think, is to understand McCarthy's definition of AI. It's the science of creating machines that can perform tasks that, typically require human intelligence.
So like problem solving, learning, language comprehension.
That's it. And you know what? That definition, formulated so early on, it still perfectly captures the field's, core aspirations.
Yeah. Very true. And, his initial work in AI, it was very much shaped by his strong background in logic, wasn't it?
Absolutely.
He developed the LISP programming language.
Yeah.
That became, indispensable for AI research.
Yeah, LISP, based on lambda calcul, it was, revolutionary. It introduced recursive data structures, automatic memory management. It gave researchers incredibly powerful and flexible tools.
Yeah, for sure.
But arguably, even more impactful was his pioneering work on formal logic, applying it to AI systems.
Right.
He demonstrated how mathematical logic, you could use it as a framework for making inferences, for solving problems through algorithms.
So this is what led to his 1959 paper, Programs with Common Sense, right?
Yeah.
That's where he introduced Situationskalkül, if I'm pronouncing that correct.
Yeah, we got it. You got it.
Which, that sounds like a truly foundational concept.
Oh, it was. It was. The key insight here, the real aha moment, is that McCarthy provided a formal, logical way for AI to understand and reason about a changing world. Oh, I see. So it's a fundamental step beyond just representing static knowledge.
Okay.
Situationskalkül, it offered this framework for AI systems to actually track how actions, how events, they alter the state of the world, and it's still a vital concept in knowledge representation today.
Wow. It's amazing how these early ideas, they still have so much impact.
Oh, absolutely. They're foundational.
So, we see this incredibly impactful career taking off in AI.
Yeah.
But then in the 1980s, he starts to shift his focus. It's almost like he's going in a completely different direction, right?
Yeah.
towards quantum technology. So what was it that sparked that transition?
Well, it wasn't as abrupt a shift as it might seem. You see, McCarthy's deep understanding of logic, of these mathematical structures, it actually gave him a very natural bridge to the logical and mathematical underpinnings of quantum mechanics.
I see.
He was particularly intrigued by quantum logic, which was developed by Gerrit Birkhoff and John von Neumann.
Okay, so quantum logic. This is where things probably got really interesting for someone with a classical mindset.
Absolutely. Absolutely. You see, quantum logic, it replaces that binary true or false of classical logic with this whole concept of states in Hilbert space.
Right.
And this opens up entirely new ways of thinking about how information can be processed.
Yeah, I can imagine.
So McCarthy, he recognized the revolutionary potential of superposition and entanglement for computation. This idea that quantum entities, they can exist in multiple states simultaneously and can be linked in this fundamentally interconnected way.
Yeah, it's pretty mind-blowing, right?
Oh, it is. And this went far beyond the limitations of the classical Turing machine model.
So was he also keeping up with the field of quantum computing, which is really starting to take off around this time?
Oh, absolutely. He was closely following all the groundbreaking ideas coming from thinkers like David Deutsch and Richard Feynman.
Yeah, those are some big names. So he's taking this deep understanding of theoretical computer science, and he's applying it to this very counterintuitive world of quantum mechanics. So how did his background in computer science shape his approach to quantum technology?
Well, he believed that a lot of those foundational concepts from classical computer science, things like the nature of decision problems, complexity theory, he thought they needed to be fundamentally re-examined when you start thinking about quantum computation.
I see.
So he was investigating how our existing logical frameworks, how they could be extended to incorporate quantum logic. But more significantly, he was exploring how quantum algorithms, they might offer huge advantages over classical algorithms, especially for specific types of decision problems, And he thought they might even provide solutions for those notoriously difficult NP-complete problems.
Right. Those are the ones that can take even the most powerful classical computers forever to solve as the problem gets bigger.
Exactly. And that's what makes the potential of quantum computing here so revolutionary.
I see. So what was the core motivation for this change in focus? I mean, he was already so accomplished in AI.
Well, he recognized the inherent limits of classical computing power, particularly when you're tackling complex tasks that he envisioned for really advanced AI, like, highly sophisticated machine learning, intricate optimization problems. And quantum technology, with its promise of algorithms like Shor's algorithm for factoring large numbers really efficiently, and Grover's algorithm for speeding up database searches, it offered this potential pathway to overcome those fundamental limitations. Because these algorithms, they demonstrated that you could potentially achieve polynomial or even sublinear time solutions for problems that would take exponential time on even the most powerful classical computers.
Okay. So in a way, he saw quantum computing as a booster for AI.
That's a good way to put.
To massively enhance the capabilities of AI.
Precisely. He envisioned transferring those efficiency gains to AI problems, like how quantum computers could drastically reduce those often very lengthy training times for complex neural networks.
Okay.
Or how they could discover better solutions for very complex AI systems.
So it wasn't just about processing speed. It sounds like he had a bigger vision. Right?
Oh, absolutely. His vision was much more expansive. It went beyond just accelerating existing computer science tasks. You see, he imagined a fundamental rethinking of the foundations of computer science itself. And he was really a pioneer in the concept of quantum AI, where algorithms, they could be not only faster, but also inherently, quote unquote, smarter.
Smarter. What does that even mean?
Well, he was thinking about leveraging the probabilistic nature of quantum mechanics.
Okay.
So he hypothesized that quantum computers, they could make decisions, but under conditions of uncertainty and with a far more robust mathematical basis than classical approaches.
Okay.
Because quantum mechanics itself is fundamentally probabilistic.
Yeah.
It offers this very natural, this powerful framework for dealing with the uncertainties that are always present in real-world AI problems.
I see.
So he truly believed that the future of computer science lay in this integration of AI and quantum technology. And he actively pursued all those theoretical underpinnings, even while the technology itself was still in its very very early stages.
So what were some of his specific contributions to this emerging field of quantum technology?
Well, one really important area was his work on developing the concepts of quantum logic.
Okay.
He explored how Boolean algebra, that bedrock of classical computing logic,
Right.
how you could integrate that into the framework of quantum logic.
I see.
He looked at the relationship between classical logic gates, those, fundamental building blocks of circuits, and their potential quantum counterparts.
Okay.
And crucially, he defined operations that could transform Boolean expressions so they could be implemented on quantum systems, but without violating those fundamental principles of quantum physics.
Wow.
And this was a critical step towards formalizing the whole design of quantum logic circuits.
That sounds incredibly complex,
Big
bridging
time.
this gap between two very different ways of thinking about logic.
It was a huge leap. Another key contribution was his work on formalizing quantum algorithms.
Oh.
He played a big role in showing that many of those core concepts from classical algorithm design, they could be adapted and applied to quantum systems.
Oh, interesting.
And he delved into those mathematical requirements for quantum algorithms to be truly efficient. And he even started to explore entirely new design paradigms that were specifically suited to the unique capabilities of quantum computation.
So he was really interested in how those quantum properties could be used for speed, right?
Mm-hmm.
For making computations much faster.
Exactly. He was focused on how superposition, that ability of a quantum system to be in multiple states at the same time, and entanglement, that spooky interconnectedness between quantum systems, how you could harness those to achieve really efficient parallel computation.
Mm-hmm.
And all of this foundational theoretical work, it really laid the groundwork for many later developments in things like quantum search algorithms and quantum optimization algorithms.
Right. And of course, there's this crucial connection back to AI.
Right.
So how did he specifically try to bring these two worlds together?
Well, he did a lot of research on how you could apply quantum algorithms to really boost the performance of AI systems.
Okay.
Both in terms of computational speed and overall accuracy.
Right.
And a major focus was on developing algorithms that could take machine learning techniques and transfer them effectively to quantum computing platforms.
Yeah.
And he looked at how quantum computers could process the massive data sets that are so common in AI. Because he argued that their inherent parallelism, it could significantly speed up the training of complex neural networks. He also investigated how quantum mechanisms could be used to build much more sophisticated probabilistic models, which are fundamental to decision-making and prediction in machine learning.
I see. So it wasn't just about raw speed. It was about fundamentally different ways of approaching problems in AI.
Exactly.
And, he also developed theories about optimizing decision processes using the principles of quantum mechanics.
Yes, he did. He explored how the non-deterministic nature of quantum mechanics, how that could be leveraged to improve decision tree algorithms and search algorithms.
Interesting.
And his theories, they were rooted in this idea that quantum logic, it offered not just potential speed-ups, but also a greater resilience to uncertainty within the data itself.
I see.
Or the problem itself. He argued that quantum algorithms could give you faster solutions and greater flexibility when you're dealing with those really complex problems that are just impractical for classical methods to handle.
So this inspired a lot of the later research into the practical applications of quantum AI.
Absolutely. It was really groundbreaking. Now, his work wasn't purely theoretical, though.
Okay.
There were actual scientific projects and collaborations that came out of these ideas.
Oh, interesting.
For example, he was involved in developing a framework for the actual implementation of quantum logic circuits.
Okay.
And this work has been used by researchers all over the world as a basis for early experimental quantum computers.
Wow.
He also contributed to the development of these hybrid computing systems.
So that's combining classical computing with quantum computing.
Exactly, leveraging the best of both worlds.
Yeah, I was going to say.
And he collaborated with leading research teams at places like Stanford University and MIT.
Big institutions.
Yeah, they were also exploring this intersection of AI and quantum technology. And he also worked closely with physicists and mathematicians. These collaborations were really crucial in translating those theoretical foundations into tangible experimental applications that were starting to emerge.
So how was his work received by, the broader scientific community? Did people embrace it right away?
Well, he was highly regarded for his intellectual breadth and for his ability to forge these interdisciplinary connections.
Right.
And his work in AI and his work in quantum technology, even if some people considered it a little ahead of its time, was widely cited and acknowledged as groundbreaking.
Right, of course.
I mean, his theoretical concepts are found in many of the fundamental textbooks on quantum technology, and his ideas about these hybrid algorithms, they're referenced all the time.
Yeah.
And his early hypotheses about how to integrate AI into quantum systems, they've had a huge influence on the current interest in quantum machine learning.
But were there any criticisms or, different perspectives on his work?
Oh, of course. I mean, some people criticized, what they saw as oversimplifications when he tried to map classical logic onto this more nuanced quantum realm.
Right.
Because quantum mechanics has its own inherent complexities that don't always translate neatly into classical computational models.
Yeah, it's a different world.
It is. And there were discussions about whether he was maybe a little too optimistic about the near-term capabilities of quantum AI, given all the technological hurdles that still existed back then, like maintaining quantum coherence.
So that's the challenge of keeping those quantum states stable long enough to do complex calculations.
Exactly. And there were also debates about how much efficiency you could actually gain with some of his proposed quantum algorithms for optimizing those really complex decision processes. But, even the criticisms were generally very respectful. I mean, his ideas, they were vital starting points for further research and development. And those debates that came up, they often led to deeper investigations and new approaches.
So even the disagreements were productive.
Absolutely. I mean, his contributions have had a lasting impact on the development of quantum technology.
Yeah.
His work on quantum logic, his early ideas about AI integration, they form the basis for a huge amount of current research.
That's incredible.
And his approaches, they continue to be applied and expanded upon in all sorts of projects, like improving the scalability of quantum computers, enhancing algorithm efficiency, refining probabilistic models. And as we've talked about, his influence was really instrumental in fostering that collaboration between computer science and quantum physics.
It's really amazing. So looking back at his whole career, what were his ultimate visions for the future of quantum technology? And what do you see as his enduring legacy?
Well, McCarthy, he envisioned a future where quantum computers could take on those incredibly complex scientific simulations. And that would lead to breakthroughs in fields that we can't even imagine yet.
Wow.
He also speculated about AI systems being massively accelerated by quantum computation and being able to model uncertainties in ways that classical systems just can't because of the nature of quantum mechanics.
Right.
And he believed that this fusion of AI and quantum technology, it could transform fields like medicine, climate research, economics.
So he was really thinking big.
Oh, huge. But he was also very aware of the ethical and societal implications.
Okay.
He warned about the potential threats to privacy, because current encryption methods might become vulnerable with powerful quantum computers. And he really emphasized the importance of responsible development, using this technology sustainably to address global problems.
So not just a technological visionary, but also someone thinking about the consequences.
Absolutely. And, his own career is a perfect example of the value of that multidisciplinary approach. He brought together mathematics, computer science, and quantum mechanics seamlessly, and he inspired a whole new generation of researchers to work at the intersection of these different fields.
Right.
And his legacy continues to inspire innovation in science, technology, and even in how we approach challenges in society.
So to wrap up this deep dive, I think it's clear that John McCarthy was a true pioneer. I mean, he not only defined the field of AI, but he also had the foresight to delve into the complexities of quantum technology.
Oh, yeah.
And his contributions to our understanding of quantum logic and those early connections he made between AI and quantum computing, I mean, they've had a huge and lasting impact.
Absolutely. And we can't forget his role as a bridge builder, connecting classical computing and quantum computing. His approach was so forward-thinking, and it's still incredibly relevant today.
It really is.
Yeah.
So here's a final thought for our listeners. Think about how the principles of quantum mechanics, they might reshape not only computation, but our understanding of intelligence itself.
That's a big question.
It is. And all of this builds on the groundwork laid by people like John McCarthy. And as we mentioned at the beginning, this deep dive was based on the essay John McCarthy, KI Pioneer mit Blick auf Quantentechnologie by Jürgo Schneppat. Thanks for joining us.